Hi, thank you for taking an interest in my work in replicating diseased artery mechanical properties. In this work, I'm focused on artery mechanical properties, how disease affects them, and how I can go about replicating this. However, for you to understand how disease affects arteries, and how I can go about replicating them in a laboratory environment, I first need to give a little bit of background on healthy artery properties. And a good comparison between healthy arteries and how they behave when stretched and pulled about is a garden hosepipe.
Now I should say that it isn't a good idea to go replacing your arteries with some piping from the garden centre, but in a few critical ways the structure and behaviour is similar. A hose pipe is mainly made up of rubber, and the main protein in arteries, elastin, behaves a lot like rubber, except a bit less stiff than in this piping here. However, another similarity comes from the helically arranged wire braiding within the hose pipe. This helps to provide a resistance at high pressure to stop the rubber bursting, and in arteries, a protein called collagen provides a similar function with a similar arrangement. The elastin, being quite compliant, allows the artery to stretch and absorb large pressures when the heart beats. But if stretched too far, such that the elastin might begin to break, the stiff collagen kicks in to provide a large resistance to any more expansion. The diseases whose mechanical properties I'm particularly interested in replicating are two of the most common, aneurysm and atherosclerosis. An aneurysm is the expansion and ballooning of the vessel wall, and much like a balloon, if left to keep expanding, the aneurysm will burst, leading to massive internal bleeding. Here is the force displacement plot before, with data for an aneurysm wall added in lighter colours. The change in mechanical response of an aneurysm wall compared to a healthy artery wall is clear. Atherosclerosis is the blocking of arteries caused by the buildup of fatty deposits in the vessel wall. The narrower vessels cannot transport as much blood to tissues, leading to tissue death, and this is especially fatal in arteries of the heart. Again, atherosclerotic artery wall mechanical properties differ to healthy artery wall. But why do I want to replicate diseased artery properties? Well, human arteries are difficult to get hold of, especially when diseased. There are costs associated with transport and proper care, as well as ethical considerations. However, pig arteries can be easily sourced from a butcher with a bit of patience and know-how. But getting pig arteries in a diseased state is far more difficult. This work hopes to solve this problem by creating disease-like mechanical properties in healthy pig arteries. Disease-like conditions are created by copying how the body alters the mechanical properties of the arteries, which is by using enzymes. The undesirable changes in mechanical properties seen in the aneurysm wall earlier can be attributed to the loss of the extensible elastin fibers. In atherosclerosis, the difference in response is thought to be partly influenced by changes in both collagen and elastin. However, in either disease, enzymes will be responsible for altering the elastin and collagen fibers. Because enzymes are very specific in what they will break down, I can select certain enzymes to digest certain proteins, in this case collagen and elastin. The arteries are exposed to the enzymes in solution at body temperature for 20 hours to ensure even breakdown of fibers. After I have treated the arteries with the enzymes, I then have to go about checking how effective the enzymes have been, by stretching the arteries and looking at them under a microscope. To stretch the artery, I cut it into several individual samples to be tested and place markers on each sample. I then place the sample into a mechanical testing machine that pulls the sample apart whilst measuring the force. I also record the sample being pulled apart using a camera so that I can later track the position of the markers to provide information on the sample deformation. The samples from healthy and enzyme-treated artery are then compared using the force required to break each sample and information on how each sample deformed. Additionally, I use microscopes and laser light sources to make the collagen and elastin proteins in the artery visible. With this, I can see if the elastin or collagen has been altered or completely broken down by the enzymes. Again, I can use this to compare between healthy and enzyme-treated samples.
This research helps understand how disease affects artery mechanical properties. It also helps to get closer to replicating disease-like mechanical properties in a laboratory environment. By reducing the cost and complexity in obtaining diseased arteries, this research aids further research into arterial diseases and treatments. I hope you found this video interesting, and thank you for watching.